recording this. Good. So again, welcome to the third and last edition of this Ringvorlesung. I want to recap a little bit what we did last time, and this time sort of go over all the essential concepts in order to prepare you to what I will tell you next. So, as I said, noncommutative geometry, so the idea is, in a sense, to replace points with states and functions with operators, okay? So in a sense, we have this operational framework that does not rely on geometrical quantities, but you can translate those geometrical quantities in operational values. And for example, here you have, as I told you from the beginning, that was the teaser I gave you, the distance function between 2 points. You can write this as the supremum of f being a C1 function, so continuous and differentiable, so one-time differentiable and continuous as well then, being, you know, mean value of omega pi of f minus omega q of f, and such that the commutative ddx of f is less equal to 1. So the norm is less equal to 1, which I told you, you know, you can replace any function by a sort of operator which acts on functions of the Hilbert space as a multiplication operator. Okay, so the spectral triple, I also explained a little bit, and this time we will go a little bit deeper into that, which is basically you have an algebra, a C-star algebra acting on a Hilbert space. I told you a C-star algebra is just a star algebra or a Banach star algebra that is complete with respect to the norm, and it fulfills additional things like the norm of A star is equal to the norm of A, and the norm of A star A is equal to the norm of A square. And then we also demand, you know, that this C-star algebra acts on a Hilbert space, and this Hilbert space, on this Hilbert space, there's also defined some self-adjoint operator D with compact resolvent, such that the commutator of D with an element of the algebra is bounded. This is the definition of a spectral triple. I will go in a little bit more into detail in showing you what does that mean. So another important definition that I gave you last time was that of an operator T on H is called a compact operator if it can be written as the sum of a lambda n, fn, gn, where gn and fn are orthonormal systems, not necessarily complete. And also an equivalent definition of an operator on a Hilbert space being a compact operator is when it maps bounded sequences into convergent subsequences, right? That was sort of, and there was then a proposition that told us, well, you can rewrite this as eigenvalue or singular values as mu n of t. So these are the singular values of t times cn cat cn bra phi n, where phi n are the sort of eigenvectors of the polar decomposition of this operator, and psi n is that of u times this operator. And we further then defined that for any alpha that is r plus, the infinitesimals of order 1 of order alpha are all such compact operators, such that, you know, you have this condition of the singular values mu of t being less equal than cn to the minus alpha for all n greater than 1, right? So just let me see what. Okay. So what is here important to state, maybe? I mean, the point is, not all compact operators are self-adjoint operators, but as I told you last time, you can do this polar decomposition by splitting it as a product of a unitary operator times this t, so the absolute value of t. And let's say it is as a positive self-adjoint operator, then this u is just simply 1, and then the mu's are simply the eigenvalues of this operator. And you see, and so you see how those eigenvalues behave for n goes to infinity, and if they behave in such a form, then they are called infinitesimals of order alpha, right? Where alpha is the order of n. The ones that we were interested in were the infinitesimals of order 1, which means that that this went so that the sum, sorry, the singular values went, you know, as, so mu n of t went as Cn inverse, right? So with for limits n goes to infinity, this is the behavior, the asymptotic behavior of that of those values, and these are the operators we're interested in. And in order to have, you know, some sort of trace of these operators, because the trace in general of such operators is not necessarily defined, right? So the trace is the sum of all eigenvalues. Let's say we have a positive self-adjoint compact operator. The trace of that means the sum of all eigenvalues, and that is not in general defined exactly because of that, you know. So it can actually diverge as logarithm of n, and the Dixmuir trace is a way to extract this logarithmic divergence for compact operators. And then I introduced something called the Wojcicki residue, which is basically an integral over those compact operators, or sorry, the differential operators. And then we basically showed this, or I didn't prove it, but I told you about it, the theorem of Kohn, that, I mean, I gave to you a few examples like the Laplacian on the tori, the Laplacian on the sphere, and the harmonic oscillator. We calculated the Dixmuir trace and the Wojcicki residue for both of them, and we saw that they both were the same. And so the Wojcicki residue and the Dixmuir trace coincide for any pseudo-differential operator of order minus n. Okay, we also define what pseudo-differential operators were and so on. But let's, I mean, just that you get the general idea of this is Dixmuir trace and Wojcicki residue are the same for certain operators, and those are exactly the operators we're interested in. And the point is also, in defining this trace, we can circumvent, in a sense, going to the integral representation, which demands, you know, a measure, which demands something like a geometry, because you're integrating over something. While on the trace side, there is no geometry implicitly in there, right? Of course, one could make the case for, well, eigenvalues are a sort of geometry, because, I mean, there is this famous paper, can you hear the shape of a drum? And I mean, you have some, you know, shape and you have a drum, and then these frequencies that come are sort of the eigenvalues of the Laplace operator. And this is actually, I mean, it's a very interesting paper. I can recommend it. So in general, the answer is no. But I mean, and this paper is in a sense a very nice example of how to write a title of a paper such that it sounds interesting for the reader, you know, and also you can remember it easily because it gives you pretty much nicely the content. Now, so the basic example of a spectral triplet is constructed by, you know, the Dirac operator on some closed n-dimensional Riemannian manifold, spin manifold as well, so it has a spin bundle and so on. Not that important. Basically, you take the algebra as the algebra of complex valued smooth functions of M, the Hilbert space to be the Hilbert space of square integral sections of the irreducible spino bundle over M with rank 2 to the n-half, where this means that you sort of neglect the ones that are not integer, and with respect to this scalar product. So you have a scalar product, you have, you know, certain functions on this Hilbert space, and you can represent, you know, your algebra there. Then you have a Dirac operator associated with this Levi-Civita connection, dx mu omega mu of the metric G. And well, I mean, I don't want to dive too much into that, but maybe just to explain a little bit, let these EAs be an orthonormal basis of vector fields related to the natural basis d mu, right? So you have your manifold, and you put a sort of tangent bundle on that manifold, and then the tangent vectors are basically these d mu, or the basis vectors of these tangent vectors. The basis vectors of this tangent bundle are this d mu, and then you have these n-binds defined, okay? And basically the n-binds do the following. They sort of rewrite a curved space-time metric into a flat one, okay? And you know the inverse, so in a sense you can also flip that thing. And okay, there is a Levi-Civita connection defined with that, a connection which tells you basically how you move, on those spaces, because, on a random manifold, it's very hard to say how to move. Of course, if you have R, you know exactly how to move by a translation. But what does a translation mean when you have a manifold that is more complex? And then, you have to take into account other things, especially since when curvature is present. And basically you have some gamma mu's, which in the anticommutator give you G mu nu of X, and you have a connection, okay, defined on that spinor bundle, and the Dirac operator is basically defined by gamma of dx mu, which is this gammas that fulfill these certain, Clifford algebra relations, connected with this delta. And basically, this is the most general Dirac operator you can, write on such a Riemannian manifold. The interesting and nice thing about this is that by the Lichnerovich formula, if you square that Dirac operator, what happens is that you get because what is the Dirac operator? The fundamental definition of that operator and why it's that important in physics. It has other reasons why it's that important in physics. In physics, basically, the Dirac operator or the Dirac equation gives you an equation of motion for particles such as fermions and so on. While in math, it had, I feel I'm not doing the Dirac operator justice. And there are, a few moments of real joy during my study of physics. No, there are a lot of moments, but moments of real wow effects, and that was one with the Dirac operator, because basically what you do is, so you have the energy relation, the energy momentum relation, which goes as this. Oh no, sorry, I already messed it up. So the famous formula, E is equal to mc squared. Now we square that. Sorry, we square that. And this formula actually only holds if the momentum is equal to 0. So in a sense, in physics, there is a relation, or in relativistic physics or relativistic mechanics or relativistic theory, there is a relation that connects the energy with the mass of a particle and with the momentum of the particle. In a certain limit, this goes to the well-known kinetic energy terms that we know from from mechanics, classical mechanics, which means Newtonian mechanics. Now, the interesting thing about this, so in quantum mechanics, we discovered if you do this correspondence principle, which means you replace the energy by a certain derivative operator, which is IH bar, where H bar is some very small constant, ddt. And if you replace P, the momentum, by IH minus IH bar ddx, and then you re-plug this into this classical equation, what happens is then that you get the Schrödinger equation for, let's say, for a particle that is moving freely, okay, without potential in this sense. So you get an equation of the form minus IH bar ddt psi is equal to minus Laplace psi. Maybe I messed up the Laplacian. No, it's good. Okay, so psi. And this is a differential equation. And when you can solve, this is it's similar to the heat equation, if you're familiar with that. And the interesting about this equation, it gives you the evolution of a particle in a quantum mechanical system. Okay. And so in a sense, because in quantum mechanics we don't have these point particles which have a definite momenta and a definite coordinate, they are replaced by these more by a wave function, basically, which in a sense the square of that gives you or the mean values of your observables give you a sort of statement about where the particle is and how fast it's moving. And now you can do the same thing relativistically, which is known as the Klein-Gordon equation. Okay, actually Schrödinger already figured that out, and he was, however, not very satisfied with it because it didn't it didn't give appropriate eigenvalues of the hydrogen atom, and thus he sort of neglected it. And then he thought to himself, oh no, this actually sounds interesting. And by that time, Klein-Gordon already published it. And here you do the same, right? So you take dt squared minus is equal to m squared c to the 4 plus the Laplacian, c squared. And now the interesting thing about, so Dirac, and then the point is that you have mg squared. So if you take the square root, to be very simple, you get a plus and a minus solution. And the minus solution, is not just as, these correspond to negative energies, and you cannot just throw them away, because in a sense that's what the equation tells you. And Dirac was thinking a long time about this, and he figured out, well, this plus minus business comes into place because you're taking the square root of something quadratic. So how about I just take the square root of this equation, and then I proceed to do my quantum mechanical considerations. And the point is, when you take the square root of that, this is exactly what the Dirac operator gives you, okay? I mean, and it is solved really beautifully. But so for this case, you have gamma mu d mu plus m, okay? And if you square that, you will see you will get a Laplacian plus an m squared. Okay, and now if you do it on a curved spacetime, you will replace your just simple partial derivatives with a nabla mu, which is the covariant derivative, which also takes into account the connection, and the gamma mu's, which are elements of a Clifford algebra, such that the anticommutator of these gammas gives you a g mu nu. And then you get an additional term which is missing, obviously, when the curvature is equal to 0. And that is the scalar curvature, right, of the manifold Mg. Good. That was a little bit of detour. I'm sorry. And now the interesting thing about this is, so let AHD, so this spectral triple, be defined as above. Then the following statement holds. Statements hold. Statement number 1, the space M is the structure space of the algebra A bar of continuous functions on M, which is the norm closure of A. Okay. Basically what that means is you have the algebra of these continuous functions, and you chose this algebra, where was it? As the algebra of complex valued functions on M. And basically you can reconstruct from the algebra the space, right? So by this famous GNS construction, or the commutative Gelfand-Naimark theorem, which basically tells you any commutative C-star algebra is equivalent to a Hausdorff space and to the algebra of continuous functions over that Hausdorff space. The second interesting thing here is that the geodesic distance between P and Q is given by, that's a Primo norm of f of p minus f of q for such that, the norm of d and f in the commutator is less equal than 1 for all pq element m, and for all f, element of the algebra, okay? So you see here, I'm talking only about algebras, structure spaces. The structure space is a space of equivalence classes of irreducible representations of A, but don't mind that. The important thing is, I'm talking here about an algebra, okay, with a norm. Here, I'm talking about the geodesic distance, which does not incorporate anything related to geometry in a strict sense. And then the Riemannian measure on M is given by the following formula. Okay, so it's the integral over M over this Riemannian manifold of F is equal to C of N trace, the Dixmuir trace, of F times D to the power of minus N. And that is, okay, C of N is just some constant that depends on N. But what is very nice about this is that, you see, we replace the integral. We replace the integral by something that only depends in the sense of an algebra and an operator. And that is the strong suit of this construction. So right, I mean, as I said, the first statement is just the Gelfand-Naimark theorem. So given a commutative C-star algebra, one can reconstruct the topological space M such that A is isometrically isomorphic to the algebra of continuous functions C of n. And what does that mean? That means you can work on this very abstract commutative C star algebra, right? And do your calculations there and so on. But then at the end of the day, you can map them to a topological space, which is also Hausdorff, and they're all isometrically isomorphic to the algebra of continuous functions. Okay, so statement 2, I already proved it to you many times. I will maybe not go through that. I mean, I will upload it. You can look at the proof, but basically it always goes, you know, it follows the same manner. You have the Lipschitz function, then you say it's less equal, and then greater equal, and thus it has to be equal. And so what is interesting, for example, I don't know what happened here. Oh, this must be this. So okay, so let's take, you know, a Riemann manifold. Maybe too much, but let's take, I mean, the real line is a Riemann manifold, right? Very easy, triple. So you take the operator ddx, and then you say, okay, this condition is equal to that, to the condition that the supreme df dx is less equal to 1, and thus a function f of x being equal to x plus constant fulfills that. And that is exactly the usual distance, because f of x minus f of y, right? So this is a solution of this, mind you, is x plus this constant minus y plus this constant, right? And thus this is equal to x minus y, which is exactly the distance. And that's, again, what is so nice about this formulation. Right, I mean, the interesting thing, which was the statement 3, is that the principle, so that this Diximy trace over this, you know, function can be represented as the integral, or other way, you know, in the other direction. The integral over a function f, you know, over this manifold can be represented as the trace. And you remember the principal symbol of the Dirac operator is gamma of xi. So the principal symbol was the leading term in a differential operator. So when we had, for example, g mu nu, g mu, g nu plus a mu d mu plus c, then the principal symbol was this g mu nu, okay? So the leading term, and in the Dirac operator, so since you have something like that, this is the leading term, gamma mu. And since f acts as a bounded multiplication operator, this f times d to the power of minus n is a pseudo differential operator of order minus n, since d to the power of minus 1 to the power of minus 1 is a compact operator and an infinitesimal of order 1. And, you know, for those pseudo differential operators, as I showed you last time, the Diximy trace and so that was proven by Kohn, the Diximy trace and the Wojcicki residue are equal, okay? And basically you just plug this in, and then you do some calculations. You take the trace here, the trace over these two-dimensional matrices, gives you this thing, and then you integrate over that, and then you get to the equation. And that is, so that's really the interesting thing about this is you don't need integrals. You don't need measure spaces in that sense. You don't need the geometry behind all those manifolds. All you need is give me the Dirac operator, and I can sort of reconstruct the whole thing. And this is really the essential idea, if you take anything with you. Right, and I mean, up till now, I mean, in every Ringvorlesung, I have sort of always showed you the same example, and I thought maybe you are slowly getting sick and tired of that. And so another very nice and also very useful example, and I will come to the usefulness later on. Sorry, my screen is getting blocked. Oh, okay. Is the space made out of 2 points? Okay, the 2-point space also called. So the space is, you have 2 points, 1 and 2, okay? Now you take the algebra. So now we want to define a spectral triple over this space, over this two-point space. The algebra is taken to be the algebra of continuous functions, where A is C plus C, okay, the direct sum over C, where any element F is a couple of complex numbers, F1 and F2, with Fi being the value of this function at the point I, right? H being a finite dimensional Hilbert space, being the direct sum over two finite dimensional Hilbert spaces, and elements of A act as diagonal matrices, okay? So that is the whole algebra. The algebra F1, you know, 1 with a unit of H1 and with a unit of H2. These are bounded operators, obviously, on this Hilbert space. And, right, and we identify the algebra with its matrix representation, right? So this is the matrix, the algebra is given by its matrix representation. And now the sort, because it's that simple, the interesting thing is that the operator has D. So we as I said, the spectral triple consists of an algebra, a Hilbert space, and Dirac operator, or a derivative operator. And this operator has to be taken as a 2 × 2 off-diagonal matrix, because any diagonal element, so if that would be a diagonal element, it would instantly vanish with the commutators of A, right? Because, I mean, you have a diagonal matrices commute, right? If the elements are commutative. I mean, if the elements that make this matter, and since these are just numbers, this has to be commutative. So in a way you can do it is you can say, because this also has to be a self-adjoint operator, so you choose 0, 0, M star and M, okay, self-adjoint obviously. And then if you take the commutator is bounded. This is also one of the conditions, and it's basically just F2 minus F1, 0, M star minus M and 0. Now the norm is basically the largest eigenvalue of this of the function absolute value of M, which is which is basically the square root of M star M, right? Because, I mean, well, yes, this is what it is. And you know, so the non-commutative distance between 2 points of y has to be, I mean, if F2 and minus Fy are such that this is less equal than 1, have to be 1 over lambda. So all these sort of, you know, distances are equal 1 over lambda. Okay. And well, it's a very nice, you know, spectral triple. Just let me put this thing here. So okay, these were the spectral triples. I will come in a minute, in a sense, what you can do with them, because I mean, up to now I showed you, well, it's nice you can sort of represent the you know, operators in or geometry in the language of operators, but how far can you take that process? Before we go to that, I want to define the non-commutative differential forms. So the differential algebra of forms of a non-commutative associative unital algebra. So yeah, if you remember your, you know, your courses of differential geometry, where you had you know, you had differential geometry, and then they define the differential forms, and you have two operators, exterior derivative, interior derivative, and the exterior derivative takes you from, you know, a vector space to, you know, the one forms over this vector space, and then you tensor them in a certain way to get 2 forms and 3 forms and so on. And it is very similar to what happens here, okay? Instead of taking a vector space, we take an algebra. And this is, in a sense, really the cornerstone of what we always, or what you know, a lot of non-commutative geometry is about. So you know, so let us describe how to construct a differential algebra over the forms. Let A be an associative algebra over C, as I said. Then the universal differential algebra of forms is just, you know, the direct sum over P of omega P of A, and this is a graded algebra, and this is defined as follows. So actually, right, sometimes you also have here a C, okay, C plus, and then you go A and plus omega 1 of A and so on, okay. So omega 0A is just the algebra, right? So the space of 0 forms is just made out of the algebra itself. And the space of one forms is generated by a so-called left A module by symbols dA. And what is really important is this operator D over here. Sometimes this operator is also called the Karoubi operator. And basically this operator does two things. It acts according to the Leibniz rule. If you have a b element of A, then d of AB is equal to dA times B plus A dB. And this is just purely definition up to now. This is just abstract, if you want to call it nonsense, right? And D applied on alpha A plus beta B, it's linear, and you can take the alpha out because, in a sense, this equation already implies that D of 1 is equal to 0. Why? Because D of 1 times 1 has to be equal to D times 1 plus 1 times D1, right? And since this is basically 2 times D1, D of 1, sorry. No, I did too many. Well, you know what I mean, right? So this is just equal to 2 times D of 1, and this is D of 1. This implies that D of 1 is equal to 0, and this thing holds for all of C, right? So the D of C is equal to 0. Now, a generic element omega of omega 1A is a finite sum of the form, you know, a I dBi, where AI and BI are just elements of the algebra. Just as is the case, you know, in the case that you know already from vector spaces, where you define one forms just as, you know, linear combinations of elements as that, where A is just the vector space, right? Okay, the left module can also be endowed with the structure of a right module. So if you have A, D, B, C, you can pull out sort of, you know, A, D, B, C. You can say, well, this is nothing else than A, D, B, C minus A, B, D, C. Okay, and now you have the D to the right, right? So in principle, we have a map D. So we constructed a map from the algebra to the algebra of one forms. And basically the one forms are those that are made out of this, right? So it is a derivation of A with values into the bimodule omega 1 of A. Why it's a bimodule? Because left and right. But okay, this is not that, maybe not the most striking of that. Now the interesting thing here is we had the algebra, right? We had C, we had the algebra, and we had omega 1 of A, or omega 1A. So omega 1A, the space of one forms, we constructed by applying this so-called Karoubi operator, or this derivation that fulfilled certain conditions. Now, the point is, how do we define P forms? And P forms can be defined by juxtaposition, just by taking these omega 1A spaces and multiplying them together P times, okay? So if you have AD A1 B0 D B1, you do the same thing, right? AD A1 B0 D B1, then you pull out the D, so you have D A1 B0 D B1, and then you subtract from that, you know, the remaining term via the Leibniz rule, and then you end up with something that is, again, you know, that has sort of two D's in to the right, and thus it is called then a T2 form. And you can define P forms basically by doing the same thing, right? And the product of a P form and a Q form produces a P plus Q form, and and omega A becomes a differential algebra by extending the differential operator D to an operator that takes you from a P form to a P plus 1 form. And this is done, you know, by just applying, you know, you take a random P form and you apply on that random P form the D, and then you get a P plus 1 form. Okay. There are two interesting things about this operator, and, you know, in a sense that this. Okay. Well, so as I said, I don't know where we got cut off, but here this Karoubi operator, or this differential operator, satisfies two things: D square equal to 0, so it's nilpotent, and extended Leibniz rule. So when you apply d on omega 1, omega 2, it is d omega 1 times omega 2 plus minus 1 over p omega 1 d omega 2, where omega 1 is a p form and omega 2 is just any, any differential form. Okay, right, and omega a is also, omega of a is a star algebra, so dA star is equal to minus dA star. And I don't want to go too much into this. There's a proof for this, and it's actually very easy to do. Maybe you can do it yourself. The A bimodule omega 1 is isomorphic to the kernel of A tensor A to A via the map A I tensor BI. Okay, and the point is, what it all comes down to basically is you can sort of relate the space of one forms with the kernel of this multiplication map. So the multiplication map basically just takes AI tensor BI and multiplies them together. Okay, so it's AI times B, right? So, or A tensor B is equal to AB. And you can represent the operator D as something that is not that abstract, but as a tensor product given as one tensor A, where the tensor product is over C, minus A tensor 1. Okay, and it's the, so that is sort of, one clue of it. So it's not just an abstract thing, but you can really, relate it to something that you can use. Okay. Now, further into this, given this spectral triple, one constructs an exterior algebra, for an exterior algebra of forms by a suitable representation of omega A. Okay, so now as in the algebra, remember we had the algebra and we had the Hilbert space, and we had a representation that took us from the algebra to the Hilbert space, and exactly the same has to happen here, and it is done as follows. The representation of a P form is given as A0, the commutator of D and A1, and so on, D and AP. And the point is, so P of, so this delta is the same as the D from before. So D A1, right? So we have some element of an algebra, A1. We apply the D on it. This gets us to the space of one forms, and then the representation of that is basically just the commutator of D with A1 for this spectral triple. Okay. And the map is a homomorphism. You can basically see that, right? Because P of A0 delta A1 blah, blah, blah is equal to P of A0, P of delta A1, P of delta of AP, right? And this is equal to A0, then P of delta A1 is D A1 and so on. Okay. And it is also a star morphism. So if you take the star, this gives you P of omega star is equal to P of omega star. And what we usually call this pi of omega 1, we call it a vector potential. So if you have a one form and you take the representation of that, that is called a vector potential. Okay. And okay, I don't want to go too much into this, but in general, let me just clear the columns. So in general, P of omega equal to 0 does not imply that P of delta of omega is equal to 0. These are the so-called junk forms. Those forms you have to factor out when you define the universal differential algebra. Okay, I don't want to go too much into that, but just keep in mind that I told you about that. So when you define now the differential forms modulo these junk forms, you can define a curvature. Okay, as you do in usual differential geometry, where the curvature is just defined, as the derivative of the connection plus the connection squared, basically. And the same is done here with the representation pi of dA plus a squared. This is what gives you the curvature. And now the scalar product of this curvature, so the square of that, gives you the so-called Yang-Mills functional. Okay, and this functional is quartic and invariant under gauge transformations. Now, for alpha being a one form and alpha being equal to alpha star, so a self-adjoint element of the algebra, the same holds for this Dixit matrix. Okay. So basically, you see, in the Young-Mills theory, I don't know how familiar you all are with that, but in the Young-Mills, you have something which is curvature, right? So let's call this curvature theta, and you take theta squared and you integrate over that to get the action principle of this curvature. And that you can replace here by this Dixie trace times d to the power of minus n. And doing that, you can get certain very interesting physical examples. So for example, I mean, one example is the standard model of particle physics, okay? So all you need is a spectral triple, an algebra, a Hilbert space, and a Dirac operator. And there comes some things called grading and so on, more to it. But basically, so the standard model of particle physics is U1 cross SU2 cross SU3. U1 describes the electromagnetic interaction, SU2 describes the electroweak interaction, or the weak interaction, sorry, both electroweak, and SU3 the strong interaction. So electromagnetic interaction basically means this group is a symmetry group of the electromagnetic interaction, and electromagnetic interactions basically describe everything that have to do with electromagnetism, which means photons and you know, sun rays and ultraviolet rays and so on. And then you have SU2. SU2 is the weak interaction, which is basically the particles that are responsible for the radioactive decay. And SU3 is the symmetry group of the strong interactions, and these are the so-called gluons, okay? So the gluons, they glue, you know, in a sense, the atoms together by gluing the proton and the neutron together. So if you have an atom, right, let's paint a very wrong picture, quantum mechanically, of that, and you have the electron, you know, doing the circles around the nucleus, and the nucleus is made out of protons and neutrons, right? And now the protons are electrically charged, so they're electrically positively charged, and the neutrons are neutral, as the name said. So there's this joke, right? A neutron goes into a bar and orders a beer, and he asks the bartender how much for that, and he says, for you, neutron, no charge. And this is exactly the point. It doesn't have a charge, but you have here positive charges, okay? And in between them, you have neutrons. And by electromagnetism, so electromagnetism usually, you know, comes into effect when you have, well, basically, when the things are very glued to each other, there you have electromagnetic, so electromagnetism gets very strong, right? And the protons, you know, would usually sort of, you know, have a force in contrary to them. So they would basically tear the nucleus apart, but that doesn't happen. And the reason why that doesn't happen are the strong interactions, and those are the gluons, okay? And basically by choosing, you know, a certain algebra, which is C infinity over some manifold, then you take, you know, the complex numbers, so basically matrices, one-dimensional matrices, the quaternions, and the three-dimensional matrices over C. Then you take certain Hilbert space and Dirac operator, and putting all that together, you can give a functional of that, which is the Young-Mills functional. And the Young-Mills functional corresponds to the action of the standard model, okay? So that is sort of very nice that it puts it in a very compact way. Are there questions so far? Because I see here. Topic. Yes, I mean, in general, that could happen, right? Exactly. Just replace the word manifold with the, you know, with the algebra, and there are certainly, you know, things where that can happen. Yes, that can actually happen for the exterior algebra. Sorry. So there are a few advantages here, and actually the space-time here, or the underlying space of this model is a product of a four-dimensional Riemannian manifold and a two-point space, exactly this one that I introduced earlier, right? So So to answer also a little bit, I don't know what's going on right now. Sorry. So also to Max's question, since d squared is equal to 0, you know, if you go from d from, I don't know, omega 1 to omega 2 of a, another d will bring you to 0, right? Because d squared is equal to 0. So that is something that one has to take into account, exactly as in the commutative case. Advantages, you know, of this non-commutative model in non-commutative geometry is are many in a sense, because, okay, so let me say 3 of them. First of all, the Higgs particle. I mean, I'm sure all of you have heard by now of the Higgs particle, and was, you know, recently discovered, and it's very important sort of piece of the puzzle for this standard model thing. And basically, I mean, if I may just very, you know, simplistic say it, simplistic put it, the Higgs, so the SU2 particles, you know, there's V plus, minus, and a Z boson. Okay, these are all bosons, and usually things that, you know, tell what do you call them, you know, communication particles. So in a sense, the graviton, which has not been discovered, is the communication particle for gravity. The photon is the one for electromagnetic waves, right? So electromagnetic waves can be understood as particles, and they're all made of, so all these particles are basically the photon. These are the things that, you know, connect one or tell one particle to another what is happening, what is the force you have to go with. And the Higgs particle gives those ones mass, because usually, you know, if you have a gauge theory, the mass breaks the gauge invariance, which is that very important, and the Higgs particle is a mechanism to put in this. And usually you have to put it in by hand, and the advantages in non-commutative geometry is it emerges as an output of the theory. Okay, it emerges as a solution of the theory, basically. So again, a Higgs particle is basically the particle that gives those SU2 particles a mass. Okay, and that is what, you know, is related to this so-called spontaneous symmetry breaking, and this can be explained pretty good in this framework of non-commutative geometry. They even made, so as far as I'm informed or remember, Kohn, Shamsuddin, and yeah, I think Kohn, Shamsuddin, probably Florian Scheck, not very sure. They made a prediction about where, you know, in which energy scale you can find it. The prediction was, however, not fulfilled. There also exists a natural cutoff. So I don't want to go into what a cutoff means. And basically, these theories are all ill-defined, and you have to somehow sum over sums that are not very well behaved. And you put a cutoff, and you say, well, we only see it to that energy anyway, so we don't need to go overboard. And usually these things are put into hand, and non-commutative geometry, in a sense, gives you a natural cutoff, and gravity can be included in those theories as well. A very big disadvantage, although, is that these theories are usually done on Riemannian manifolds, while real physics happens on Lorentzian manifolds. So this is, you know, in a sense, a very big disadvantage of those theories. Okay, now, for the last few 40 minutes, I would like to tell you about another very interesting subject of non-commutative geometry, or of non-commutative algebras, which is called the deformation quantization. Basically, if you know, I would have to explain it very simply. Deformation quantization means you take an algebra and you deform it by some sort of a power series in such a way that this deformed algebra still fulfills, you know, algebraic elements, algebraic properties, and if I set the parameter of which this deformation depends equal to 0, you go back to the original algebra. Let me give you a concrete example. Let's say, sorry, I think it's already okay. Let's say you have an algebra given as the algebra over all continuous functions over some compact manifold, and the pointwise product. Now this, these two things give you a commutative algebra, right? Now I can take this algebra A again, but replace its pointwise product by a so-called star product, which is non-commutative but associative, okay? So if I take two functions, let me first tell you what this product does. Well, I can already tell you that it's non-commutative, which means F star G is not equal to G star F, as is in the case of the usual pointwise product, right? X squared times sinus of X is the same as sinus of X times X squared, right? The order is not that important, but here in the star product it is. And it is given as the exponential of the sum over some skew-symmetric matrix times the nabla with respect to X, the nabla with respect to Y, on functions f of X times g of Y, and at the end of the day we set X equal to Y, okay? So it's a power series. The nice thing about this is, you see, if I set theta equal to 0, so, okay, in the sense, this matrix is just, a matrix given by some, deformation parameter, let's call it theta, it's some real parameter, and then 0, 1, -1, 0. So this standard symplectic matrix, as they call it. Okay, the epsilon tensor in 2 dimensions and so on. And if I set theta equal to 0, this whole matrix is just 0. Then it's the 0 matrix, the n cross n dimensional 0 matrix. This makes this 0, and thus you just have f of x times g of y. For x equal to y is f of x times g of x. Okay. Now, as I said, the interesting thing about this is also it's associative. So f star g star h is the same as f star g star h. And it has also interesting integral representations, okay? And so the integral representations are basically those, but this is not the one that I want right now. Let me skip that. Well, okay, the interesting thing about this is if you take now x mu and x nu, okay? I take the coordinates, x, and I take the star product. So the star product is just, the function x mu exponential times x nu. And now that I do a power. Oh, sorry. What I'm getting. Oh, good that you ask. Right. Oh, wow. Sorry. I didn't. I'm sorry. I cannot see the chat instantly. Yeah, actually, Maximilian put it perfectly. A Lorentzian geometry has just, is negative definite. So for example, we live in if you neglect curvature, we live in the case of, we live in a Lorentzian manifold, namely the Minkowski spacetime, and it fulfills certain properties, and it actually can be described by a metric of the form -1, +1, +1, +1. And that is contrary to the usual Euclidean space where you have +1, +1, +1, +1, okay? Their distances are also mean different things, right? So a distance in the Euclidean space is clear, while a distance in the Minkowski space is not that clear because the distance function is not necessarily positive definite, okay? So thank you, Sandra, for this question. And thank you, Maximilian, for answering it. So now here I do the star product, right? X mu equal to I theta rho sigma d rho d sigma x nu. And now I do a Taylor expansion, okay? So the first term is 1 plus, the Taylor expansion of the exponential is 1 plus x squared divided by 2 factorial and so on. And so I break it up at the order of theta to the second. So theta to the second, I would usually have here I squared divided by 2 factorial, theta rho 1 sigma 1, theta rho 2 sigma 2, d rho 1 2, d sigma 1 d sigma 2, right? On the other side. The point is that, okay, the first one is just x mu times x mu. The second one is I theta rho sigma. And now I do the derivation of x mu. The derivation of x mu with respect to rho is delta rho mu. It's just the Konica delta. And then here it's delta sigma nu. And I have here equal to 0 because the derivative of delta of something constant is equal to 0. And then I have, so x mu star x nu is equal to x nu plus I theta mu nu. I do the same thing with the other way around. So nu mu. Then I get x mu plus I theta nu mu. If I take the commutator of these two, right? So the theta commutator of these two, I get x nu is equal to 2I theta mu mu. Now, the interesting thing, so why am I doing all this nonsense with the non-commutative star product? It is so in quantum mechanics, as I told you in the beginning of this lecture, you have the commutator of so let's say let's just take 2 dimensions, x and p equal to I h bar, right? These are self-adjoint operators, unbounded, giving on some dense subspace of some Hilbert space. Now, so here there are operators, right, working on infinite dimensional space. But what I can do by using this star Moyal Vi product and by setting theta, the deformation parameter, equal to h bar, and the coordinates being, the coordinates of the space and of the momenta, I get now. So let me denote, these are operators. Now these are just classical functions, but instead of taking the commutator, which doesn't make any, makes sense, the commutator of classical functions is usually 0, right? But for the theta case, so for the star product, this is equal to I h bar. Okay, so in a way, I can express the non-commutativity of quantum mechanics by using just usual phase space functions with the algebra defined over them and replacing the usual pointwise product by a star product. Okay, this is basically what, so for physicists, why we take interest in that star product. And also there's also, quantum mechanically, so okay, we have 2 fundamental pillars in physics. One is the quantum part, quantum mechanics, which basically tells you, how restrictive the usual measuring process is, right? So it tells you delta x times delta p is greater equal than h bar half. So the uncertainty with which you measure the space coordinate times the uncertainty with what you measure the momentum coordinate is greater equal than h bar half. And on the other hand, you have general relativity, which tells you, in a sense, how space-time curvature relates to gravity, and actually it's the same thing. And also it predicts, there are solutions of general relativity of the Einstein equations, which are given by black holes. And in principle, a black hole, so I hope I get this right. Well, some constants, okay? Let's forget all the constants and let's take the things that are important. Basically, a black hole is, you take a mass and you squeeze that mass down to a certain radius, and when the proportion of 2m divided, or when 2m divided by r becomes equal to 1, then there's a gravitational collapse and you create a black hole. For Earth, this is, I think, a few centimeters, and for the Sun, it's 3 kilometers. So if you take the whole Sun, which is pretty big, and so I think it's 10 to the 30 kilometers or something, and you just squeeze it into 3 kilometers because of the high gravity that this object then has on a very small point, there is what we call a sort of a gravitational collapse, and the thing is a black hole. So you have a sort of an event horizon, and some singularity where it's not that clear right now what that is. But basically, this is what a black hole is. Okay, and now if you take those two together, then you see actually it is not possible to put enough energy, because to measure a particle you have to put enough energy into that particle. So let's say you have an electron floating around, and you want to measure that electron, and you want to do it very precisely, and you put a lot of energy up from a certain point. So by taking these two principles, the energy you have to put into this measurement creates in itself a black hole. Okay, and this is sort of a contradiction to what we see on a day-to-day basis. And thus you can replace actually the space-time continuum by a non-commutative space-time, which in a very simple case is given by that one. Okay, and I mean, these effects are sort of, maybe noticeable by, at a certain length called Planck length square, which is like 10 to the minus 34 meters. It's a very small quantity, okay? And in those series, it's also important. So what is interesting about the star product, it fulfills the following conditions. If you take the commutator of f with g with respect to the star product, it is equal to theta times I of the Poisson bracket. So things that people know from symplectic mechanics and so on, and Dirac as insightful and smart. I mean, smart doesn't describe Dirac quite well. As he was, he guessed actually that, in a sense, because he noticed that the commutator relations look a little bit alike like the symplectic structure of the Poisson bracket, and so he thought to himself, well, they have to be connected somehow, and he guessed sort of the first order of such a deformation quantization. Okay, now, so of course, if you divide now by this theta and you send theta equal to 0, you get the symplectic structure, the Poisson bracket. Now, an equivalent integral representation of this star product is given by so you take the integral over the translation of f by u, by the variable u, the translation of v of g of x by v, and you integrate over du dv, and here it is e to the I theta u times gv, where g was this matrix, this general symplectic matrix, basically, right? Where the ones here are sort of dependent on the dimension, and you can you can pretty much write it in this way. So it's just an integral representation of this very weird exponential thing. The point is, first of all, I mean, I haven't talked about convergence, okay? Because you see, this is an infinite sum. In what sense does that converge? In what sense, is that formal? So in a, I'm getting this, sorry. Okay. And so in order to know what this, so I just got a warning somehow he cannot record longer than 40 minutes or something, and in 10 minutes he will kick us out. I'm sorry, I'm having technical difficulties today, so we will have to go back and do this thing again for the rest of the 10 minutes. Okay, so right, if f and g are elements of the Schwarz space, then basically these integrals are well defined, okay? And even if f and g are elements of continuous functions that have bounded derivatives, we can actually show that this exists. And now the idea was, and one of the ideas, and I'm sorry for making it that short, and I hope it's not understood as an insult, but you can generalize it to a C-star algebra. You can generalize this star product to a C-star algebra. So instead of taking elements of just functions, you can take C-star algebraic elements, and that has very interesting mathematical consequences. Right. Now, to tell you a little bit, about physics and things that happened, and developments that actually are very new. Grosse and Lechner, so Harald Grosse is a professor at the University of Vienna with whom I did my master thesis. He worked, and he's working on this subject of quantum field theory, and actually he showed that non-commutative quantum field theories have a lot of advantages, in regards to renormalization, that thing that I told you about. You have these sums and you don't know how to control them. And he constructed a model which is known as the Gosser-Vulkenhaar model, which basically kills a thing that is called the Landau ghost. I don't want to go into it, but this is something that just happens because of non-commutative quantum field theory and not, because of anything else. Good. Now, they were able, so in 2007, they were able to define a quantum field on a non-commutative Lorentzian spacetime. So basically a Minkowski spacetime with a metric of the form -1, 1, 1, and 1, right? And then later on, and these quantum fields, usually when you have non-commutative spacetime, since you don't have a notion of a point, you get in trouble with causality. Okay, so that is a huge advantage of relativistic quantum field theory. It tells you basically how to how to measure things, and in a sense, it takes into account that the light of velocity, the speed of velocity, so the speed of light, the velocity of light or the speed of light is constant in all initial systems. Okay, this is a fundamental principle of relativistic mechanics, and what relativistic quantum field theory tells you is that if you have two quantum fields, phi x and phi y, okay, describing the dynamics of a particle, of a relativistic particle, usually a boson. Actually, I mean the same thing holds for fermions and so on, but let's be very simple here. And they are space-like separated, which means basically that you, in a sense, they cannot causally influence each other, since the speed of light is the maximum velocity that we have. Then phi of x and phi of y commute. For, I mean, x is the point, x and y is the point. Now, if you don't have, x and y, you don't have points, what does that mean? That means basically that that condition, the causality, doesn't hold anymore. And that is a huge setback for non-commutative quantum field theory. However, in 2007, Grosse and Lechner were able to relate these fields living on non-commutative space-times with fields which are called wedge local, and they fulfill certain locality and causality properties that are weaker than the ones that usually are fulfilled, but stronger than not having them at all. And then, it was noticed that this A theta, the way they deformed these fields, was connected to the so-called Riefel deformation. And the Riefel deformation was the one that I told you, about. So this deformation, like the deformation of products of C-star algebras. And it is defined in the following way. So, or it is connected in the following way. The products of two Riefel deformed operators, A theta and B theta, is given as the non-commutative product of Riefel, A theta, A cross theta, so times theta, B, and the whole thing deformed again, where A theta is just given by some cutoff function, forget that for the moment, e to the minus xy, the translation with respect to theta x, and the translation times u of y, dx dy, where u of x is just, a translation with some operator q mu, that is self-adjoint, and thus this is a unitary group. And this is the adjoint action. Okay, alpha y is the adjoint action, which if a was a function, it would do exactly that what it's supposed to, it translates. Okay. And, oh yeah, perfect, actually. So, right, so Buchholz and Summers proved that in 2010 rigorously, that the Riefer deformation is somehow connected with these deformed fields of Grosse and Lechner by the formula A theta B theta is equal to, you know, the Riefer product of A with B, and the whole thing deformed again, and the deformation is given by that. Okay, now I will tell you a little bit what we can do with that. Before that, I think or maybe, wait, let me see if I can stop